Okay, so now I have a logarithmic equation that I need to solve. The argument is my variable, right? The argument of the logarithm has my variable in it. And so kind of the parentheses of my logarithm here are the castle walls that are keeping me away from the variable that I need access to. And none of my typical tools, none of my standard tools will work. I cannot get to that x. And to solve this equation, I have to get to that x. And so I'm kind of in a quandary here because I have to get to it, but none of my typical tools will work. And so I have to remember what a logarithm and an exponential function, how they're related to each other. A logarithm and an exponential of the same base are inverses of each other. And what that means, if two functions are inverses of each other, that means if I compose the functions, they undo each other's work, right? And that's the same thing as f inverse of f of x equals x. The input is the output. The input is the output. And what that means is if I can find the inverse function to this log, I can undo that log and I can be left with x there. I'll just have to, whatever function I run this side of the equation through, I'll also have to run this side of the equation through. Now, a logarithm and an exponential of the same base are inverses of each other. That means that log base 5 of x, log base 5 of x and 5 to the x are inverses of each other. And so that means that 5 to the log base 5 of x equals x, and log base 5 of 5 to the x is x. That's by the definition of inverse functions. Okay. Well, it looks like this is what I want, right? Because I want to take my log base 5 of x and I want to peel the log base 5 away and just be left with the x. And so 5 to the x is going to do that for me. And so I need to run both sides of this equation through the function 5 to the x. Now, these are going to undo each other. That's the whole point. And I'm going to be left with x equals 5 raised to the 4. Now, 5 cubed was 125, so 5 to the 4 is going to be 125 times 5, which is going to be, 600 and another one. Yeah, it's going to be a big number. So I'm going to do 5. I'm going to be a little bit lazy. I'm going to do 5 raised to the 4 here and get 625. Hey, I was close. Was getting there. You can reason your way there. But sometimes it is nice to be able to just go there and get an answer. Okay. That worked. So let's try another one. Let's try a slightly harder problem. See if we can reason through it the same kind of way. Let's look at something like log base 2 of 10 plus 3x equals 5. Once again, my variable is hidden within my argument of my logarithm. I cannot peel that back using any of my old tools. I cannot get rid of that using any of my old tools. I must use an inverse function. The only inverse function we're going to find for this, for log base 2 of x, is going to be an exponential with the same base. And so it's going to be 2 to the x. This is log base 2 of x. This is exponential base 2. And so to get an exponential that's an inverse of a log, they have to have the same base. And so for this, I'm going to run 2 to the x. I'm going to run both sides of that equation through 2 to the x. And so these are going to undo each other just as I want them to. And I'm going to end up with 10 plus 3x equals 2 to the 5th. Okay. That I ought to be able to solve. 2 to the 4th is 16, so 2 to the 5th is going to be 32. Double check myself on that, but 2 to the 5th should be 32. And so what am I going to have? I'm going to have 10 plus 3x equals 32. I'm going to subtract the 10 from both sides. To get rid of it on the left side, I'm going to have 3x equals 22. X equals 22 over 3, which is as simple as I can write that. Or 22 over 3, if I want a better feel for it, it equals 7.3 repeating. I should check my value here when I plug that in, that this stays positive within the argument of my logarithm, because otherwise I'm out of my domain of my logarithm, and I can't actually find that. But since that is, and 625 is positive and works up there, I'm actually quite good. No, 6.3 repeating, 7.3 repeating. Now, how could I check this? Well, I'd want to graph it, right? I'd want to graph the left-hand side and the right-hand side. On the right-hand side, that's easy. That's just 5, right? And I'd look for the intersection between that and this curve. The problem is I still don't have a log base 2 button on my TI-84 style calculator. And so I'm going to have to use that change of base function, or the change of base formula again. So I'm going to do natural log, because I have that button, 10 plus 3x. And then I'm going to divide that by the natural log of 2, right? Because that's my change of base formula, is the log of the new base of the argument divided by the log of the new base of the old base. Okay, and so I'm going to graph that and look for the intersection of those two. And if I'm looking at that y value, yeah, somewhere just above 7 seems reasonable. And if I use my intersect tool, I find that 7.3 repeating is going to be my answer. And so I've used my calculator to check and verify that I did this correct algebraically. Okay. If I wanted to make this just a little bit more difficult, let's do one more difficult kind of example here. So let's look at the log of 2x plus 1 and subtract from that the log of x minus 2. And that's going to equal 1. And I want to solve that for x. I can't just run to the trick that I've been running to, right? Because this is a common log. And so kind of the log of x is log base 10 of x, right? And so that means that 10 to the x is the inverse function that I want here. But I can't just run both sides of this equation through 10 to the x. Because that's not as friendly, right? I suppose I can, because then I could break that exponent up into, 10 to the first one times 10 to the negative second one, and I'll get there. I'll get there eventually. I think it's just a little bit cleaner before I do that to use one of my logarithmic properties, right? And so I kind of had that first logarithmic property that was log of mn is log of m plus log of n. And then I had that second property. It was log of m to the p is p log of m. And then kind of that third property, and this is the one that I'm really looking for right now, is log of m divided by n is the log of m minus the log of n. It's an n. Okay, well this is one minus the other, so I can turn that into a ratio. And if I turn that into a ratio first, it's just a little easier, it's a little cleaner. And so I'll have log of 2x plus 1 over x minus 2 equals 1. And now if I run both sides of that through 10 to the x, I'll end up with these undo each other, right? Because they're inverse functions, that's the whole point. And I get 2x plus 1 over x minus 2 equals 1. 10 to the 1, sorry, 10 to the 1. And so I'm going to multiply both sides by x minus 2 to get rid of that denominator. I'll have 2x plus 1 equals 10 times x minus 2. I'll distribute that 10. 2x plus 1 equals 10x minus 20. Now I want to get all the x's on one side, all the numbers on the other. So I'm going to subtract 10x, subtract 10x, subtract 1, subtract 1. And what am I going to get? I'm going to get negative 8x equals negative 21. X equals 21 divided by 8. And that's positive, and 21 divided by 8 is greater than 2, right? And so that will stay positive, and 21 divided by 8, that will stay positive. And so I've got a good answer within the domain of both of my functions there. And if I want to test this, well, what can I do? I can go back, I can graph these, and I can do log of 2x plus 1, and then I can subtract from that log of x minus 2, and then I can set that equal to 1. I can graph the two, and I can see that 21 over 8 is between 2 and 3, which makes sense, right? Because 24 would be 3, and so between 2 and 3, that seems reasonable. And so I got 2.625. Now if I do 21 over 8, I get 2.625. So also equals 2.625. All right. I hope that helps us in working these kinds of equations.